Hello and welcome. In the last video, we had a discussion about a combinational error verification using System Verilog version of UVM. Now, here in this video, we will try to take one sequential example, and we are taking the DUT as a data flip-flop, D flip-flop, very simple, and we will try to verify that with the help of System Verilog version of UVM. So this is what the test bench architecture for that. So here, as you can see, we have one TB top. Inside that, we are declaring the instance of the interface and DUT. Then it has the test we are running within initial begin view. Now the test class is there, in which sequences are we have declared a sequences, sequence 1, sequence 2, and sequence 3. And then it has environment. So environment has the scoreboard, which is used for comparing our input and output to produce the result, test pass or fail. And it has an analysis implementation board, as we know. Then agent we are considering, which is an active agent. So it will have all the three essential components like sequencer, driver, and monitor. As you know, the driver responsibility is to drive the stimulus to the DUT with the help of this interface. So this driver has the port which will get the sequence, this sequence with this sequencer. So the sequencer is just a mediator between sequence and driver, and sequencer has this export, and we are making this connection inside the agent connect phase with TLM, transaction level modeling. On the other hand, the monitor component, which is responsible to capture the information from this DUT through this virtual interface and broadcast this data to multiple components. That's why it has one analysis port. And we are broadcasting this data, just we are sending this data to a scoreboard here. Only one component we are connecting, hence this monitor is just sending this data, captured information from this DUT through this interface to the scoreboard, and scoreboard getting this with this analysis implementation. So this is what the complete test bench architecture. Now let me show you the complete code for this, verifying a sequential circuit called the D flip-flop. This is for the DUT, which has clock reset and D in and one D out. So whenever the reset is 0, output will follow input. So D out will be equal to D in at every passage of the clock. This is what a simple RTL which is written in System Verilog. So input logic clock reset and input D in, then output logic is D out. Always at the rate passage of the clock, always underscore FF at the rate passage of the clock. If reset, we are making output is equal to 0, else we are saying output should follow the input. So output is equal to input. And this is what the AND module D flip-flop. Now let me show you the interface definition. We are considering a simple interface. We are not considering the mod ports and clocking block here. In the next video, we'll try to see that. So this simple interface logic, we are declaring all the inputs and outputs of the logic type here in interface. Inside logic, clock, reset, D in and D out. Simple, very simple. Now let me show you the TB top. So this is what the TB top, right? So here TB top is there. So over there we are just instantiating the D flip-flop interface. So D flip-flop name interface is a name, VIF the instance for that, and empty parenthesis is mandatory. Now the RTL instantiation, our DUT instantiation, so name is DFFRTL and just instance name is DUT, we are D. And inside that, within parenthesis, just we are making the connection of this clock with this clock reset and input and out using order based method. Now within initial begin block, first we are making the clock as 0. Then in the config DB, we are setting the virtual interface, as you can see. Okay, so using set method, we are setting the config DB, and as you know, it has 4 parameters: null, first, and this within double quote we are giving the star. So this will visible for entire test bench architecture. We can access in entire uh, architecture to this interface. And the key is virtual INTF and the variable is VIF. Okay. Now here only just we are calling this run test method. So this run test method will execute will initiate to execute all the phases starting from build phase to the final phase. And just we are generating a clock here, always hash of ton VIF is equal to not of VIF. Very simple. Now let me show you the transaction class for this. So this is what two lines are mandatory in order to access the UVM macros and UVM package, meaning classes. Then the transaction class, which is just keep a track of all inputs and output of the DUT. So as you can see, class sequence item, which is extending from UVM sequence item. And for inputs, we are making them as a rand. We want to use the randomized facility of System Verilog. And then this is the D out, which is output, and we are not making it as a rand, just we are declaring it as a bit type. Okay. Now here just we are using the factory registration macro and field factory registration and field macros for all the inputs and outputs. Okay. And as it is a component class, its default it's an object class, so its default constructor expecting one argument only. Now let me show you the sequence class. So we are using three sequences here. Sequence 1 is for reset is equal to 0, and sequence 2 is for reset is equal to 1, and sequence 3 is for random inputs like reset and all. Okay, now here class sequence 1, which is extending from UVM sequence, as it is a parameterized one, we have to parameterize with the type of transaction. This is an factory registration macro, object factory registration macro. Then its default constructor with one argument. Inside a body, the executable logic we need to write inside a body, because this object class does not have the phase concept. So inside this body, first we are creating the object for REQ, which is an inbuilt object of the transaction class, and we are repeating 5 times this random value. Inside that we are a start item, we are defining the start item and finish item, and inside that we are randomizing, and just we are making this reset is equal to 0, and just we are printing a message like data sent to driver, and just using the print method, inbuilt print method, to verify what the data it is generating. Okay. Now inside a sequence 2, which is also similar, just we are here making this reset is equal to 1. The rest of the things are same. And in the sequence 3, which is also extending from UVM sequence, entire things are same, just we are making all the inputs as a random value, like that reset and D. So as you can see over here, you can use tick UVM do also to perform the job of this 3 line of code: start item, finish item, and this one randomization. Now let me show you the sequencer class, which is just a mediator between this sequence and driver. So just a mediator, hence just factory registration macro and its default constructor. As it is a component, its default constructor expecting 2 arguments. Now the driver class, as you know, the driver responsibility is to drive the stimulus to the DUT. Okay, so with this interface, right? So as it is a class based environment and interface as a static component, we have to make it as a virtual. So first driver, which is extending from UVM driver, it is also a parameterized class, so we have to parameterize with the type of transaction. And here we are declaring that virtual interface, virtual DIF, okay, DFF IF interface, right? D flip-flop interface, and instance is VIF. As it is a component class, so component factory registration macro and default constructor with 2 arguments. Now in the build phase, just we are creating the object for this REQ using factory script method, and we are getting that interface here, which we have already set in the top module, right? TB top. So if it is not of config DB, then we are printing a message tick UVM fatal that unable to get interface. So as also as you know that dit set and get will expect 4 arguments. So in this get method, we have to provide this empty double quote and the key, whatever we have set it, and the variable VIF, right? Now inside the drive task, we have to drive a logic, right? We have to drive this reset and D in to the DUT with the help of this interface. So within this forever begin block, we are first writing sequence item port dot get next item and sequence item port dot item done. Inside this, we are writing the drive logic. So REQ dot reset and D in, we are applying to the DUT with the help of this virtual interface. So left hand side should be VIF, right, for driving this stimulus, and we are using non-blocking assignments for driving. And just we are printing the message, that's the data, send data to DUT, and just printing using print method in order to verify what transaction we are sending to the DUT. And after this item done, we are waiting for two positive edge of the clock. You can write this line after this print method also, meaning before this sequence item port item done also will be same, will get the same output only. So in the run phase, which is main phase, just we are calling the drive task in which we are driving this stimulus to the DUT. Okay, nothing else. So another class is the monitor class. The monitor class responsibility is to capture the information and broadcast this to multiple components. So here we are, it is not a parameterized one, hence we have to declare the instance of the transaction class trans and we virtual interface, right? And it has one analysis port, right, that we have to declare here. So UVM analysis port, which is a parameterized one with the type of transaction and name is AP. And it is and as it is a component class, we have to register with component details and default constructor with two arguments, right? And just we are creating the memory, allocating a memory for this analysis port with new construct here. Inside a build phase, just we have to create the object for this transaction object trans using factory create method. And here also we are getting this virtual interface. If not able to get, then print the fatal. Print this message unable to get interface using tick UVM fatal. Now inside task capture, we are capturing the information from the DUT through this virtual interface. So the right hand side should be virtual interface, and we are capturing this into trans object. So same delay we have to give, which we have given inside the driver. So repeat to at the rate pause of the clock, and we are capturing this information, all inputs and outputs in this trans object, and just printing a message send data to scoreboard. And we are just using a print method to print the collected data. Now that collected data we have to capture that data into analysis port. So how to capture that? An AP object of analysis port dot write method. Inside this transaction we have all collected data, so we have to put this data inside this analysis port to send this to the scoreboard, right? In the run phase of that monitor, just we are calling that capture task, nothing else. Now inside a config class, next is a config class where we are declaring the agent, declaring the one parameter called is active, which is of UVM active sv-uvm, and we are making it as active UVM active. So it will meaning the agent will be active only. So which it will have all the essential components like sequencer, driver, and monitor. Okay, and as it is an object class, we have to register with object details and its default constructor expecting one argument. Now inside the agent class, we have to declare the instances for driver, sequencer, and monitor, and this agent config, and we are creating in the build phase. As it is a component class, we have to use factory UVM component details, factory registration macro, and default constructor with two arguments. Now in the build phase, we have to create the object for monitor and then agent, and we are checking that if it is an active agent using this tick UVM config db, okay, which we have set it in the top class, which is a test, right? I will show you that later. We are getting that if it is an active agent, then we have to create this driver and sequencer. In the connect phase, we have to make a connection between this driver port and sequencer export, which is there in the agent, right? Driver has a port and sequencer has export. So inside the build phase, we have to just make use of this connect method to make a connection between export of this sequencer with this port of this driver. Very simple. Now the scoreboard, which is used to do the comparison. Here we have to declare the analysis implementation port, and which expecting two arguments. First one is a type of transaction, and second argument where we have to declare that implementation logic. So we have to declare that we are declaring in the scoreboard only. So take second argument is a scoreboard. The name is analysis implementation port we are giving. Okay. Now it is also component, so it's default constructor expecting two arguments, and we have registering with sv-uvm component details. And inside the build fetch we are creating the data which we have declared here, right, with sequence item type, transaction type. And in the write method, which is a void function, inside that we are just declaring the instance for this sequence item t, and just we are printing the message like data received from monitor analysis port, and using the print method to print that whatever we are receiving. And we are writing this comparison logic, very simple. If the reset is equal to 1, then we are saying this the reset input is detected. Okay, reset dff reset input. Else if reset is equal to 0, meaning not of reset, and output is equal to input, then we are saying test is pass, else test is fail. Very simple logic. Now inside the environment class we have to declare the instances for a scoreboard and agent, and we have to create both of them in the build phase. Okay, and registering with the tick uvm component details and default constructor with two arguments. In the connect phase of that, we have to make a connection between this analysis implementation port of in scoreboard and the analysis port of the monitor. So as you can see, this connection we have to make in this environment. Scoreboard has analysis implementation port and monitor has analysis port, right? So we have to make a connection with the analysis port, because we have to make with the initiator. So initiator is a monitor. So we how to make a connection? This agent has this monitor, right? Agent object dot monitor object dot analysis port dot connect to the scoreboard analysis implementation. Very simple. Now inside the base test class, we are declaring the instance of this environment. Okay, and then this instance for this agent config, right? And as it is a component, take uvm component registration micro and default constructor with two arguments. Now inside the build phase, we have to create the objects for this environment and agent config. And here we are setting that, right? Take uvm config db agent config, and we are setting this, right, agent configuration here to make the active or passive agent. Right, inside the end of elaboration phase, just we are printing a topology in order to verify our test bench, complete test bench architecture. And inside the report phase, just we are printing the message like test fail or pass. If the UVM fatal and UVM error is greater than 0, then we will saying the test is fail, else test is pass. Now inside the test one, which is extending from base test, we are declaring the instances of sequence 1, 2, and 3. And as it is also component class, we have to register with factory registration micro and default constructor expecting two arguments. Inside that, just we are calling this build phase, right? Which is the will call to the parent method. So the parent for this is base test, right? Inside we declared a logic for creating the environment and config db. So no need to write again and again. Just we need to call this parent build method, build phase, right? And in the run phase, which is the main phase, we are creating the instances for all sequences, sequence 1, sequence 2, and sequence 3. And here we are raising objection and dropping objection. And we are starting the sequences one by one. Sequence 1 is start onto the sequencer, which is there in the agent of environment. Similarly, after giving some delay, we are starting sequence 2 onto the sequencer, which is there in the agent of an environment, and so on. 3 sequences we are starting. Now we are ending the test 1, right? And already we have explained, already I have explained this top module and all, right? Now let me show you how to get the result from this. So Verilog file name is project1 dff uvm.sv. So we'll see the output. We'll observe the output here. It will take some time. Let's observe the output. Okay. So test is passing, meaning there is no any UVM error and no fatal. So zero UVM error, zero fatal, hence test is passing, right? Now we'll try to see from the top, like from the sequence. First we'll see the topology, what the topology is printing. Okay, let me show you that. Okay, so this is what topology. You can find the top component is test. Inside that agent is there. Sorry, environment, and environment has this agent and scoreboard, right? So agent is an active agent since it has driver, monitor, and sequencer, all three essential components, right? And driver has this port, and monitor has this analysis port, and sequencer has this analysis export, right? Similarly, scoreboard has this analysis implementation port. Okay. Now here first sequence in which we are declaring the reset as a 0 and d in is random, right? So d in is equal to 1. So driver is driving that same data, reset is 0 and d in is equal to 1. So as you can see, monitor we are capturing that d is equal to reset is equal to 0, d in is equal to 1, output is equal to 1. So same we are getting in the scoreboard, meaning we are getting the expected one, and test is passing. And we are repeating the sequence one 5 times, so we'll get 5 times of the sequence one message, right? So similarly for reset is equal to 0, d is equal to 1, and so on. Now let me show you the interesting one, like where sequence reset is equal to 1, so that is sequence 2, right? So inside sequence 2, let's try to understand this. Okay, so here the reset is equal to 1 and d in is equal to 0, right? So output should be 0. So as you can see here, output is equal to 0. And in the scoreboard, we are printing the message DFF reset input, right? Similarly, here D in reset is equal to 1, D in is equal to 0 only. We'll see anywhere if D in is equal to 1, right? So you can see in sequence 2 only, reset is equal to 1, D in is equal to 1, right? So output should be 0 only because reset is 1. And driver, you can see it is driving same input. And monitor we can capture reset is equal to 1, d in is equal to 1, and output is equal to 0. The scoreboard is also capturing same information. Now similarly for sequence 3, let me show you sequence 3. Here you can see reset is equal to 1, random inputs, reset 1, d in 1, out, and d out. So at the driver we are driving this 2 input and capturing the same input and output at monitor. So you can see reset is equal to 1, d in is equal to 1, output is equal to 0. Similarly for sequence 3, let's see any other information, like here random inputs 0 0 0. So a driver 0 0 only, and monitor will also get output is equal to 0 and expected one, hence test is passing. So this is what the complete verification of the D flip-flop. In the next video, we'll try to understand the same D flip-flop with mod ports and clocking blocks, and also we'll try to add the virtual sequence and virtual sequencer concept. So with this, I hope you have understood this video and you'll get the clear flow of the UVM for verifying any sequential circuit. So you can explore more about this by taking this example. And I also hope you enjoyed this video. So thanks for watching. Thank you.